First of all, I have to explain what I will be talking about. We all know what a permutation group is, but I should, just to be safe, define what is meant by diameter, particularly the diameter of a group. So given a group and given a set of generators, I can define a Cayley graph. So this is a graph whose set of vertices is just a set of elements of the group, and I will connect two vertices, that is two elements of the group, if their quotient is in the set of generators. Now, by definition, because the set of generators is a set of generators, this graph will be connected. There will be always a way to go from, say, the identity to any element of the group, just by taking products. Now, the diameter of a graph, in general, the diameter of a graph is the longest shortest distance. So you define the distance. So I'm giving right now verbally a definition that turns out to be equivalent, but not the same as the one there. So I'm reminding you of the definition of the diameter of a graph in general. So you define the distance between 2 points as being the length of the shortest path between them, length being the number of edges in that path. And then, well, how do you define what is the diameter of say, a disk? Well, it's a distance between the 2 points that are furthest apart. The same way in a graph, the diameter of the graph is the distance between the 2 points that are furthest apart, whose distance is greatest. Well, I could also define the diameter quite specifically of a Cayley graph as follows. I can express any element of the group as a product of generators, by definition. That's what makes them generators. For any element, there's the shortest word or the shortest words. There might be a tie. So the cost of the element G is the minimal number of generators that that you have to use to get that element. And then I find the worst element, what is the most expensive element, and that cost is the diameter. Well, it's a very simple exercise to show that these two definitions are equivalent. The definition for a Cayley graph is the same as the special case of the definition of the diameter for a graph. No? So in other words, when I'm asking what the diameter of my Cayley graph is, I'm asking how good or how bad is my set of generators. I can express anything in terms of it, but can I express everything as a short word in it or not? So a diameter could be very small. The set of generators, I mean, any group has a set of generators with respect to which its diameter is 1, namely G. It could also be really, really large compared to G for certain kinds of group C. Now, say that G is Z mod n Z. Oh, I actually detest this notation. Well, never mind. So say I have C mod n Z, and I have the generators plus minus 1. Then the Cayley graph is going to look like that. Plus 1 in this direction, minus 1 in this one, and so forth. So it's going to be a circle, so not a disk, a circle, and so this will have a very large diameter, because if this has n nodes, then the distance between this and that is going to be n½ There's no way, no shorter path than this one. No? I mean, if you want to generate Z mod 2016 by ones, then you have to express 1013 as the sum of 1013 ones. That's, well, it is a number system, but not a very good one. So the diameter there is very large. It's linear with respect to G. In general, if G is abelian, then most of the time you will be able, or even nilpotent, you should be able to find generators with respect to which the diameter is very large. But what happens if G is not abelian? If it's not nilpotent, what happens if you are far away from that? In practice, it would seem that diameters have to be small. As in, it was conjectured, and we will see that in a moment, that if G is the contrary of abelian, if it's non-abelian and simple, and finite, then the diameter with respect to any generators, even if the devil chooses a set of generators, and we're not friends with the devil, the diameter will be small. So, I mean, this is what makes puzzles good. I mean, if Rubik's Cube took longer than the age of the universe to solve, it would not be a good puzzle. The point is that you have this complicated group, but you can also get from any position to any other valid position with a small set of moves. It's really hard to find. You know, many brave people died. No, they did not die, but wasted a lot of time trying to find the diameter. But the diameter turned out to be really small. So it's 20. And it has been known for a long time that it was not large. Very well. No, so the diameter is tiny compared to G. And that's actually a typical situation for a non-abelian group. That's actually not, this group is not simple or even transitive, but it's getting there. All right, so I define the diameter of a group to be the worst case diameter. So for the devil set of generators, the diameter. And the conjecture, it's a conjecture of Babai's, that when G is finite, simple, and non-abelian, simple being, of course, that it cannot be decomposed into smaller groups, then the diameter is going to be it's going to be polynomial on log. There's going to be an absolute constant C and an absolute implied constant, such that the diameter is bounded by the implied constant times log to the C. So this has been proven for quite a few groups. So, well, I proved it for PSL2P, then for PSL3P. That took a lot of work, and much of that work was quite general. This was also generalized, well, to other ground fields. I should also say, even though it doesn't fit quite in this framework, that also on the topic of generalizing the ground field, there was related work then by Burgan and Gambert on SU2, which at the level of Lie algebras is the same as SL2, but then you're working over complex numbers and you're trying to prove slightly different things. Well, there was work to, at the end, the broadest generalization known for linear algebraic groups is that this sort of statement is true, independent of P or of Q. That was always the case, otherwise the statements would be void, for all groups of Lie type of bounded rank. So we have Babai's conjecture for groups of matrices, but C still depends. I mean, we believe it doesn't depend, but in the results that you get, C depends on the rank. That is, the rank of SLN is n-1, so it depends on the size of your matrices. So one problem is to try to obtain independence on the rank. Another problem is to consider the problem of pure rank, if you wish. So what about alternating groups? Say, you have permutation groups. Sim_n is a group of all permutations. Well, that's not quite simple, so we pass to all 10, which is of index 2. You have the 15 puzzle. It's not solvable precisely because all 10 is not Sim_n. So you have a group of index 2 in Sim_n, you consider that. Very well. And all 10 is really the evil permutation group in many ways. So can you get any sort of result for all 10? The classification theorem, by the way, gives you an additional reason why you should care about all 10. So in the classification theorem, whose proof, of course, you have heard, would take an entire encyclopedia if it were all written down in one place, says that the finite simple groups are the matrix groups, basically. Well, sometimes with really funny twists. Then the alternating group, and then some horrible groups. It's a zoo of monsters, but it's a finite zoo. There's a finite number of monsters. So that means that we don't care about the monsters because we are looking for asymptotic statements. So any asymptotic statement will not be affected by a finite number of groups. Well, only the implied constants will be affected, but nothing else. So we can just focus. If we want to prove things for all finite simple groups, if we want to prove Babai's conjecture, we can just focus on A and B. So what remains to be done then is what is the diameter of all 10? And of course, what bounds can you give on the diameter of matrix groups, simple matrix groups that do not depend on the rank. Those problems turn out to be intimately connected. So, all right, here's my bound with Seress from a few years ago. So this is not polynomial on log G. Polynomial log G would be the same as polynomial on n. This is quasi-polynomial on n. So it's e to the log n to a power, e to the log n to the fourth, basically. So e to the log G to the fourth. And in fact, all 10, I said it was the hardest. I really mean this in a strong sense. Once you have that, using classification, you get all permutation groups. You get a dependence on n. Yeah, and I should say, allergy warning, that the proof did use the classification theorem. All right. Now the situation was not completely satisfactory. It's not completely satisfactory yet either. For several reasons. First of all, of course, you would like to have a bound that is of the quality of Gauss conjecture, so a power of log. So a power of log of G, that is a power of n. And also there's the fact that many of the consequences of this kind of results were not consequences directly of the diameter. They were consequences of what I proved to get to the diameter. I proved a product result. And that was used by Bourgain-Gambert and by many other people to prove expansion results. So product theorems are nice in and of themselves. This is the most general. So this is what I proved for SL2, SL3, and what has been proved in full generality by Piber-Szabo and Bruyère-Grintao. So there exists C of R. So right now it's still, it depends on the rank, such that if you take any set of generators of G, then either A times A times A, that is the set of all products of three elements of A, is intergroup, or A times A times A is greater than A by a power that depends only on the rank R, nothing else. No? So for bounded rank, you just have A cubed is greater than A to the 1 plus epsilon. So you get this, well, it's not quite exponential, but you get this very rapid sort of growth. So you just have, in order to prove a diameter result from this, you just need to apply this theorem log times, right? Because you first apply it to A, so you get that A cubed, if you wish, is greater than A to the 1 plus delta. Then you apply the same result to A cubed instead of A, so you get that this is this A to the 1 plus delta squared, and so on. So you get that A to the 3 to the k 1 plus delta. And at some point you have to stop, because this would get to be larger than the size of the group, and that's impossible. So then you know that at some step, possibly the last one, you must have already got that A is 3 to the k, then is all of the group. And then you get this means that the diameter is at most 3 to the k. Right. Very well. So I corrected myself while speaking a moment ago. I said that it's not that, yes, that as far as we know, C of R depends on the rank. But here you actually have a dependence on the rank. So in the diameter, we believe that one should be able to give a polynomial on log bounded diameter that depends on pretty much nothing, that is independent of the rank in particular. But in the case of product theorems, in the case of theorems of this kind, then it's inevitable that delta depends on the rank, at least if you want precisely that statement with no modifications. No? You can give examples, these are due to Piber and Spiga, in the alternating group, where A generates G, but you have A cubed is barely bigger than A. It's bigger by just a constant factor. And you can give closely related examples to that in groups of n by n matrices. And there's also the problem, so it's not just that the goal, unmodified, this intermediate goal would be false, but that many of the techniques that were developed it's completely unclear how anything like them could work in a symmetric group. So, I was proving all of these intermediate results where I was saying, well, suppose that A barely grows. I mean, other people call these approximate groups. It's basically the same notion. Then A has these beautiful properties. Eventually, these beautiful properties get used to show that those sets don't exist, of course. The intersections with varieties are exactly of the size or of the order of magnitude that you would expect even the dimension of the varieties. This is actually analog, as was remarked by Rinthao, to what Larson Ping had been proving before, not about A sets A that barely grow, but sets A that don't grow at all, that is subgroups. But never mind. Well, of course, the problem here, as when time comes to try to generalize what's called escape from subvariety, which is very closely connected, the problem is that, well, what on earth is a variety in Cm? It's completely unclear. Or in the case of n by n matrices, you can define these varieties, but their degree blows up, their complexity blows up. Well, it increases, and rather the bounds you get from these techniques have a complexity that blows up when the dimension grows, when the degree grows. So, yeah, in retrospect, you know, why were Seress and I even trying? But we managed to do something. At any rate, so even though it's impossible to get product results of exactly the same shape as for SLN and bounded, we would like to have them, or results like them. So let me tell you about what my aims for today are. So I would like to explain a simplified proof of Helfgott-Seress. I believe it's much simpler. It's gradually getting simpler. And I will show you in particular that this proof, unlike Helfgott-Seress, does give you a product theorem, a slightly weaker looking product theorem. It has to be, but still something that is from which you can deduce the diameter bound. Now, I'm not claiming right now that I have improved 4. Also, so 3 should not be taken here to be an attained goal. And 4 is something on which Piber has been working. And so I started to talk about these things with Piber, and then Piber said to go our own way. So Piber is working on 4. I do not know where. I don't think he's ready to claim something there either, though I think he's a very clever person who has lots of ideas. So I will be talking about 1 and 2. All right. So this is what I prove. Yes, so you do get a product result, which is, so that exponent is basically 1 plus a constant over log n. No, it's very slightly worse than that. And then, so you either get that that is true, or you get that you have managed to reduce things to a smaller group, a group with no large alternating factors. No? Very well. So it's an immediate corollary via Babai-Seress that you get from here a bound like that in Helfgott-Seress. Well, in fact, it's worse by a factor of log n, but at least you get it as a result of the kind of result that I really wanted. Also, a small note. I do know, in fact, Piber and I realized that there is a gap in Babai-Seress, and if you fill it, it's easy to do, then the exponent increases by 1 in all of the literature that depends on Babai-Seress. But there's actually a way to modify the statement of Babai-Seress so that the bounds in the literature, including Helfgott-Seress and including these, don't actually get worse. Very well. So I talked about dimensional estimates, so let me show you what they actually are before I try to do anything that looks like a generalization. So I said that in SLN, in SL2, what you have is that if A barely grows, then the intersection of A with just about any variety is what you would expect it to be. Well, let me explain what I mean by that. So you have SL2, you have a one-dimensional variety of SL2, and then the intersection, we say, if A barely grows, so either A grows, in which case we are done, or the the intersection with V is a to the 1/3, basically. A to the 1/3 plus O of delta. 1/3 being the dimension of V, 1 divided by the dimension of the group. No, so it's like saying, well, I have this blob, it's not a stick, it's a blob, and so when I put some sort of, I don't have a stick here. If I put some line through it or a curve through it, imagine my blob, I'm going to be really violent, so I have a blob here, then, you know, the bit of the stick that will be full of goo or blood or whatever will be about the volume of the blob to the 1/3. This is what's saying. What is he saying? This is saying that any set A that doesn't grow much will have to be like a blob, not like some sort of unspeakable fractal thing or a line or what have you. It's not flat either, it's a blob. Very well. So how on earth can you speak of blobs in a symmetric group? Well, it turns out that you can actually deduce this from a completely abstract statement just about groups. So you can say, well, and this issue is proved by the simplest of combinatorial means. Basically, you're proving inequalities here, like there. You're proving that a set is smaller than another by constructing an injection from the first set to the second set. So you can say that this set on the left grows after just one step. When you just multiply it by itself, it grows with respect to R unless the denominator is large. So, of course, this, as I said, it's an elementary statement. You might wonder, well, but what is its meaning beyond its consequence here? Well, you can extract consequences from that in the symmetric group. No, so, and you can extract consequences from that using the same sort of philosophy. The issue is that, so you're think of V, a variety. What does it mean to be in a variety? It means to be special in some way. That's also what escape from a variety means. You want to escape from special conditions. So very generally, you could have some sort of being special in the symmetric group, like and you would like to use the fact that you have something special to conjugate, take intersections until this denominator becomes trivial. And there you must have growth. This thing on the left is bigger than R to the 1 plus 1 over K. So what is special, so two examples of special sets in the symmetric group are things of a kind that, well, are studied all the time in permutation groups and that in particular appear in my work with Seress, namely pointwise stabilizers and setwise stabilizers. And also you have all of this notion of orbits. No? So an orbit of an action is just, well, the orbit of a point under an action is just a set of things to which your group is sending things, but you don't have to look just at a group or at a subgroup. You could look at a set, A and G, no? And if G is acting on a set X, you can just look at the orbit X to the A, if you prefer A to the X, of the point X. So this is the orbit of a point under A. And in a permutation group, yeah, you have orbits, and orbits could be huge. They could be all of the set that the permutation group is acting on, be, you know, squares in a Rubik cube or the numbers 1 up to n, or they could be small. So the point, so what you get is that if by special, you mean that you could make special mean having no long orbits. And if you do that, then you get something non-trivial. You get that if you have a set R such that R squared doesn't have long orbits, so it's not even sitting in a necessarily sitting in a stabilizer, it just doesn't have long orbits under this, the 1 up to n has no long orbits under R squared, then R, after being conjugated by a few things and multiplied by itself, grows. It's larger than R to the 1 plus a constant over log n. And this is related to some statements in Helfgott and Seress that in turn generalize some things by Babai, but here you can derive it from scratch from the very simple statement in the previous slide, and in a way that is really analogous to the dimensional estimates for linear algebraic groups. No? So it's just as before. When R is special, then either R grows or R is really small compared to A. Well, you can, I'm compounding here what I just said with something trivial. All right, so then even though I should say that this work, like my previous work on the symmetric group, is not constructive in the sense that it doesn't show you how to solve Rubik's Cube, say. Just it's about, or it's the same for linear algebraic groups. You get diameter bounds, but even in SL2, we have, for just completely generic generators, we have no idea of how to attain the really good diameter bounds that we have. Well, even though these things are not constructive, it turns out that many ideas from constructive or even computational permutation group theory are useful. So in particular, there's something that is not in itself necessarily computational, but that should be familiar to anybody who has ever carried out computations with permutation groups. It's the idea of having a chain of stabilizers. I used the word stabilizer before. So a pointwise stabilizer for a set of points is just a subgroup of G consisting of the elements that fix every single point. Whereas a setwise stabilizer would be the elements of G that fix the set as a set. They could permute the set. Well, and of course you can create a chain of stabilizers. You have G, you consider the stabilizer of a point that's smaller than the stabilizer of that point and another point that gets smaller, another point, and so forth. Very well, that's what's called a chain of stabilizers, and you say you have a base when you have a set of points such that their pointwise stabilizer is trivial. All right, so let's choose our alpha 1 up to alpha j greedily so that the orbit is maximal at every step. So you have stabilized some things, but you might still have long orbits, so you pick a point with a long orbit and you stabilize that. And you stop when there are no long orbits left. So by this special set lemma that we were talking about when we were studying blobs, this set has to be smallish because it has no long orbits, or either that or it grows. And the only way that a set like that can be smallish, I mean, this can be proven, this sounds wrong, but it can be proven trivially by pigeonhole. The only way that a set of the form A inverse times A can be small, A inverse times A is not small, we're comparing things with A, but the only way that a pointwise stabilizer, even with respect to, say, k points, of a set of the form A inverse times A can be small is if k is large. Because in general, what is going to be contained in your pointwise stabilizer? It's any quotient of two elements that send these elements to the same tuple. So if k is not too large by pigeonhole, you're going to have lots of such pairs of elements. All right, so this shows that this chain has to be long, at least a constant times log a over log n squared. Very well. And then you take a setwise stabilizer. And for this, just to be clear, it's not, I mean, it's completely irrelevant, but you can reorder your things so that alpha 1, alpha 2, alpha j minus 1 are 1, j minus 1, because then I can actually draw things on the board. No, this is what's called the prefix and the suffix. So it's really alpha. But you could say it's 1. So you're going to have these things. And you have that the pointwise stabilizer here, that is a long chain. And the pointwise stabilizer here is sort of smallish. And this will be pretty large, the prefix in the setwise stabilizer, because the orbits are long and because j is large. So in fact, when you restrict here the setwise stabilizer, here, this is called the prefix, it's going to be such a large subset of the alternating group here on these elements that it will have to generate a really large alternating subgroup of these. Moreover, how is this also useful? Well, we care about the setwise stabilizer and the pointwise stabilizer in part because we care about actions. And conjugation is a particularly nice action. And the set-wise stabilizer acts on the point-wise stabilizer. So this is a set-wise stabilizer where, interesting things happen here, and interesting things happen here, but things here don't go over there. That's the set-wise stabilizer. And the point-wise stabilizer is when this is all fixed, and interesting things just happen here. But then this acts by conjugation on that. And when you have an action, you ask yourself, how does the action make things grow? No? When you conjugate things here by things there, does the set of such things here get bigger? Very well. So the suffix has no long orbits. What about, sorry, I said suffix before when I meant prefix. This is a prefix as a suffix, of course. So what about the group generated by the set-wise stabilizer? Well, if it has no long orbits, this is a group. So a group like that has no long orbits cannot have large alternating factors. And then you can use induction, as I said before. You can pass down by Babbage-Serres to smaller alternating groups, and you get an inductive process going. So suppose it does have long orbits, then what do you have? What you have is that, well, first of all, without rushing, what happens if the diameter is small? Why do you have an inductive process? Well, by induction, you can construct, the diameter of that smaller alternating group is not too large, so you can construct any element you want. In particular, you can construct, well, magical elements that allow you to win just like that. Because what is a magical element? An element of support no bigger than n over 3. Once you have an element of support no bigger than n over 3, you can construct supports, you can go down in support very quickly by conjugation. This is something that appears, well, in several places, but in particular in Babbage-Serres. And then you get a polynomial bounded diameter polynomial in terms of the diameter of that smaller alternating group that I told you about. So if you can pass to a smaller alternating group, you're done. Now, what happens if you can't? Well, if you can't, then that means that the group has a long orbit. So here, this group has a long orbit, the group generated by these things. But your set here has no long orbits. But then you are precisely in the situation of the spatial set lemma. You are basically sitting, you're, say, in an alternating group, and you have a set inside that does not have long orbits with respect to the size of that group. Very well. But that means that that set must grow. This set must grow. Are you done? Well, not quite yet. I mean, it is a completely standard thing that growth in subgroups implies growth in the groups. But that just means growth by the same factor. So growth here by s to the 1 over log n. So that might be a problem if s is really, really small. If we were very, very successful when we were constructing this prefix and we went on for so long that this became tiny. Because even though the growth here will be very large relative to the size of s, it will be small compared to the original set of A. But then an argument that is already done in Helfgott-Serres works, because, well, so we modify things a bit, and we get that you have an expensive set of bounded size that generates a group. Here I get a somewhat bigger set that I can get more cheaply. No? So I can get some generating elements here that generate something with a large orbit. That's good. And then what do I have? I have that, well, no element of you cannot just commute with every set, every element of a generating set of a group, unless, well, you are actually in the center of the group. If you were in the center of the group, that would mean basically that you are pure prefix and you fix everything else. But that would be an element of small support, and you would be done, as I said before, by this descent, this very quick descent by Babbage-Serres. So suppose that's not the case, and every element of the prefix has to act non-trivially on at least one of the log n generating elements. But that means that when you conjugate this by that, then this becomes pretty big. So it either becomes much bigger than it was, or, well, at least this means that S is at least of size of the prefix to delta over log n. And you obtain growth. No? You obtain growth by at least a factor of size to the prefix to delta over log n log n. And that's it, basically. So let me give you a summary of some of the moral. All right. And this is the moral not just for this talk, but the moral for the entire process that started in 2005. I said the paper appeared in 2008 for SL2, but I wrote it in 2005. So many elementary statements in group theory are true not just for subgroups, which is how they are usually stated, but for sets. Well, is that nonsensical? No. What happens is that you can make them for sets. They are strong statements for subgroups, but they are also strong when you apply them to sets that grow slowly. So say you can get, the orbit stabilizer theorem, which we call a theorem because for undergrads it's theorem sized. It's actually a lemma, but it's an extremely useful lemma. It's already extremely useful when you do it for subgroups. But in fact, you can prove it for sets. It's no longer an equality. It's two inequalities in different directions. They are not quite the same thing, but they are pretty close to the same thing. So it's pretty tight if A grows slowly. So you do that. And you can rephrase everything since SL2 in terms of these sort of results. So the orbit stabilizer theorem. Also, you should think not just, so why do I not use so much the word that other people use, approximate subgroups? Because I think that, from my perspective, one should view things even more generally. If one wants to give some sort of formal framework, it's not just about groups acting on themselves, it's about groups acting on sets or groups acting on objects. So in particular in groups, so in the action matters a very great deal. You already get some interesting things when you just consider the action consisting of multiplication on the left or on the right. But things really get going when you consider the action by conjugation. And that's a very interesting action of the group on itself, because the orbits are interesting, they are conjugacy classes, because the centralizers are interesting, they are commutators. But here as well, you can have a subgroup acting on another subgroup by conjugation. You have a set-wise stabilizer acting on a point-wise stabilizer by conjugation. Very well. So the reason why a fairly great deal of really elementary group theory can be adapted in that way is that it is extremely concrete. So quite a bit of late 19th century, early 20th century, or mid 20th century group theory was actually algorithmic without knowing it, so to speak, or it was unconfessedly algorithmic. This is how people worked. They didn't have computers, but they wanted to compute things, or they proved things by actually showing what these elements in the group were doing in permutation groups. Group theory at first was not very abstract, it was extremely concrete. And this is precisely what enables one to generalize it to sets. I should also say that you have the probabilistic, what is called the probabilistic method. It's not really a method, it's more of a general idea. No? So you want to show that elephants exist, or you want to show that there's an elephant in the room. So you prove that if you pick a random person in the room, he's a secret elephant with positive probability. Hence, there are elephants in the room. Well, what happens if you're not in a room? What happens if you are in this vast place, in the Calanque? So you cannot just get to every point in the room just like that. In fact, that would solve the problem of diameter. But what you want to show is that if you take a random walk around here, you will find an elephant. Well, wild boars, all these are much more common here, but you will find an elephant or a wild boar with positive probability. Hence, there are wild boars in the vicinity. And you actually do that. So you take random walks. This is what you do in the symmetric group. And this is what compensates to some extent for the fact that you have much less structure in a permutation group. So in matrix groups, you are able to get quite a lot of mileage from the fact that you don't just have the action of the group on itself by conjugation, you also have the action, of course, the action that defines matrix group. Matrices are ways of writing actions on affine space. So you have this beautiful geometric action, this meaningful action of the group on a space that is not much smaller than the group itself. It has a lot of structure to it. It's not just the action on a set, it's the action on a linear space. So that's how you get varieties and so forth. Well, in the symmetric group, you don't have that. You have something much less structured in some ways. At the same time, you do have an action on a set. It's just a set, it doesn't have structure, it's just a row set, but it's a set that is much smaller, much smaller than the group itself. If your group is, you know, like, say, the evil group, or the alternating group, that is really at the heart of everything. But its very smallness, the fact that you have this complicated action of something very small, save the day, because that means that because you have something fairly small, not bounded but small, 1 up to n, short random walks of size polynomial on n, will randomize things completely, almost perfectly. And a power of n is really small compared to the size of the group, because the group is of size n factorial or n factorial over 2. So you can afford that. And I should also say that I hope that, well, I mean, why am I keeping on working on permutation groups? Well, lots of people care a great deal about that, and I have grown to care about them. But it is also the case that I feel that once we simplify and conceptualize matters enough for permutation groups, we will finally be able, I hope, to make progress in the case of unbounded rank for linear groups. Why? Well, this is some sort of mystagogical statement, but many people who are wiser or more initiated than I am agree that it's true. They have religious wars as to why it's true or exactly what it means, but they do agree it's true. So, namely that Simen, some would say all 10, but say Simen is the symmetric, it's SLN over the field with one element. So this is mystical. The field with one element, for some, the field with one element doesn't exist, but objects defined over it exist. For other people, it does exist in some indirect way, but they don't agree on exactly what it is. However, people do agree more or less on what objects defined over the field with one element are in practice, and so even different schools of thoughts agree that this statement is true. And in this sort of context, in this very practical context, I do believe that this statement is true. This statement behaves as if it were true, in the sense that the problems in SLN for n unbounded are in part the problems in SLN for n bounded, and those we know how to deal with, at least in principle, and in part the problems for Simen. And you can see that quite clearly. Say, the counterexamples for product theorems in SLN are almost permutation matrices, or you can modify them so they are no longer that, but it's clearly that they are really tightly connected to the obstacles for the symmetric group. And, well, you do have stabilizers and so forth in matrix groups, and my aim in simplifying things is to make it possible or plausible that we will be able to, any of us will be able to make progress in matrix groups of unbounded rank, which is still the other major open problem in this particular field. And that's it. So, just what I said. Very well.
Okay, thank you very much, Harald. Are there questions, remarks? Please speak in Dutch.
Yes. Just perhaps a substitute for this mystical statement about the symmetric group being SLN over the field with one element. How about simply what dimension do you need in order to embed the permutation group on n elements?
Well, you need about n, yes.
I think that's a simpler mathematical statement.
Sure, but the mystical statement is stronger, and I think at least I believe in its consequences. We should behave as if it were true.
Okay, are there more? Yeah. Wait a minute, please. Wait a minute until you have this, just to record, because they are recording everything. So. Mind what you are saying now.
Just give us some information, so it's yeah. So I'm just curious if you can get any bounds on spectrum of those Cayley graphs on permutation groups. Maybe not. Something like expander bounds.
Sure, not expander bounds. You get something weaker. You get any diameter bound is going to give you a bound on the spectral gap, but it will not be a constant. And it cannot be. I mean, there are generators of symmetric group with respect to which symmetric group is not an expander. In fact, the hard thing is to construct an expander. Whether, say, a random pair of generators would give you an expander, there's no consensus on that. And of course, yeah, it's unknown, and we don't even know what to believe. Yeah, and the product theorem also should give you a slightly less. Yeah, so one of the good things about the product theorem is that you can get a stronger, but still not extremely strong spectral gap bound directly from a product theorem rather than from the diameter result.
Okay.
But that's in general true for any group. So.
Okay, are there more questions? Yes, Jean-Louis?
So if you have, sorry, if you have factoriality or absence of factoriality, the diameter could be different.
Factoriality?
What is the role of absence of factoriality on the diameter?
Yes, so, so why do we care about simple groups in particular, or no, rather?
In general, probably not.
Well, actually, so most of the time, if your factors behave nicely, then the diameter of your group can be bounded in some way by the diameter of the nastiest factors. But you could have some funny actions. I mean, you need to be really careful with that statement, because you could have some evil actions. Say in permutation groups, of course, if you don't assume transitivity, then you can get a huge diameter just by taking, say, the group that is just, either that is generated by a cycle on 1 and 2, and then a cycle on 3 elements, and a cycle on 5 elements, 7 elements, 11 elements, you get a horrid diameter. So, but in permutation groups, if you assume transitivity, the diameter can be bounded, and this is by Shedish, in terms of the diameter of the largest factor, the largest alternating factor.
Okay, thank you.
Okay, thank you. More questions, remarks? Okay, if not, then thanks again.